Our final piece of atomic theory has to do with something called quantum theory. It's not a whole new thing, it's kind of the most modern take on what we've been studying all along, and that's atomic theory. Before I get you into quantum theory and what's called quantum numbers, I want to just kind of give you a quick recap so that we're all picking up where we left off. The last thing that we talked about was what Bohr added to the model of the atom, and that was with the flame test and the electrons jumping up and down, and those sorts of things. From excited to ground state, some of the things that we looked at with the glasses and the spectral lines from the different gas tubes and the bands of color that were being given off, and all the things that Bohr observed and tried to explain with his rendition of the model, and that's what you see here. The Rutherford-Bohr model, or what we sometimes think of as the planetary model, where we have a nucleus, kind of represents the sun, and then the planets around the nucleus, we represent the electrons in very distinct rings. Just like the planets have orbits that are very specific, Bohr's model has the electrons at very specific distances from the nucleus and not in between. So that's kind of where we're picking up and where we're adding on to from there. The fellow who gives us, or sort of leads the team that gives us the quantum theory part of atomic theory, is a fellow by the name of Herman Schrodinger. And here's his picture. He's got great hair. Goofy looking fellow. Like the glasses. I like the hair too, actually. And he's famous in the early 1900s. So we're getting up to within the last 100 years now. And Schrodinger, an Austrian, along with a number of other people on his team, was very big into math. And so the math really, this is where the rubber meets the road for all those mathematicians. They're going to put a lot of probability and calculation to what we've been looking at all along. From more of a qualitative perspective, they're going to quantify a lot more of it. We're not going to look at their math, but there's a lot of math behind it. What Schrodinger and his team believed is that electrons don't just move in these simple spherical orbits around the nucleus, like the Bohr model would say, but that those electrons are moving often in various shapes, some of them very complicated. And what he came up with then is what we call the quantum mechanical model of the atom, quantum theory, and quantum numbers. When you hear the word quantum, essentially quantum has a fairly broad meaning, which means a very tiny unit of something, in this case, unit of energy. It has to do with how the electrons move within the atom, how they excite from one level to the other. It's all kinds of different sort of applications of the word quantum. Don't worry about that right now. Think about quantum theory as energy theory. That's kind of the simplest way to think about it. What quantum numbers and quantum theory give us is that we can predict the location of electrons down to what we call an orbital, or that's more or less a region of probability. You're going to hear the word orbital a lot as sort of the area where we would expect to find an electron in an atom, or the path of an electron within the atom is called its orbital. So it's almost like orbit, but orbital. And so it's kind of along the lines of that motion or that path of an electron. Schrodinger's work gives us a set of 4 quantum numbers. And those 4 quantum numbers that are unique for each electron in an atom tell us about its motion, or how it's moving, and its position, or where it's at. Think back to physical science, where you heard a lot about the energy of position and the energy of motion. Well, here it is, quantum being energy theory, energy numbers that describe these kinds of energy of the electrons, motion and position. Wolfgang Pauli, around the same time, another Austrian, formulated and gives us what we call today the Pauli exclusion principle, which says that no 2 electrons in a particular atom can have the same set of 4 quantum numbers. In other words, you're in an atom with me, and let's say everyone else in the class is in an atom with me as an electron. Each of us has to have our own set of 4 quantum numbers that makes each of us unique in terms of our energy and our motion and our position. And so the Pauli exclusion principle says that no 2 electrons can share the same set of numbers or have the same set of 4 quantum numbers. Think about the 4 quantum numbers kind of like you might think of a ticket for a major sporting event or a concert at a big stadium. So for example, as you see here, this is a ticket for a football game in 2011 between the New York Giants and Green Bay Packers. I don't remember how this game went down. I suspect it was cold. It was early December in New York, or New Jersey. In any case, you see here there's lots of information on the ticket, including the cost. You can see here it's almost $300 for this ticket. But the important thing I want to point out here is across the top you'll notice there's a section a section number, a row number, a seat number, all those things that we kind of designate as we're trying to go into an event. Maybe even something like a Civic Center concert ticket would have the same sort of information. But this is for an even bigger stadium, so it includes a fourth piece of information. And that's not always the case with something like a Civic Center, where it mentions the gate, tells you which door to go into this huge stadium. So we're going to start with that. A lot of people, if you go to an event like this, will go through the same door, through the same entry, through the same gate as you. That west gate that you see here, you go through there with this ticket, so will thousands of other people go through that. In an atom, we don't have gates that tell us where the electrons are. What we have are what we call energy levels. And those rings that we see on the Bohr model are kind of represented here. The first quantum number isn't the gate like you'd find on a ticket, but we call it the principal quantum number. And we're going to go into more detail on each of these quantum numbers briefly as we go into this next video or two. But the first quantum number tells us which of those rings, as you see here there are these 7 rings around this black nucleus, which of those is the electron in. So that's a very kind of introductory way to start narrowing it down. Okay, I'm in the first ring, or I'm in the third ring, or I'm in the fifth ring. And those are the energy levels that we call that, the distance from the nucleus. The second number at the top here you see is the section. The section in a stadium is big. It's going to have hundreds of seats in it, but it's narrowing it down a little bit. Lots of folks go through one gate. Only a few hundred might go to your section. Well, in an atom, we have something kind of like a section. We call it an orbital. And in this case, the second quantum number is called the orbital quantum number. And it will tell you not which section of the atom to go to necessarily, but it will tell you the three-dimensional shape of the electron's path as it moves around in the nucleus. So this is going to narrow it down for us a little bit further. Now again, we'll go into more detail on these quantum numbers in a little bit, but the second one tells us what we call the orbital shape of the electron's path. The third quantum number represents and kind of goes with here in our ticket example again. While there might be hundreds of people in your section, there's only probably a couple dozen in your row at the most, maybe 20 or something like that. In this case, this is row AA. All right. If you're in row AA in a stadium, that's probably the 27th row up off the field. In an atom, we're going to zero in a little more specifically to within that orbital then, what is the three-dimensional orientation? Okay, and we'll get into this more later, but we call it the magnetic quantum number. It tells us if the electron is moving in a path that's in the x-axis of the atom, if it's in the y-axis of the atom, or if it's in that sort of in and out depth z-axis of the atom. And you see here, you see the XYZ axes on this diagram. It's kind of along that line. So that's what the third quantum number is all about. And the final number on your seat, or on your ticket rather, is your seat number. So this ticket says you're seat 12. And hopefully when you go through the west gate to section 235, row AA, and you get to seat 12, you'll find there's no one else sitting there. Because if there is, what the heck, they're in the wrong seat, right? Or else you're in the wrong place. Let's assume you're in the right place. They must be in the wrong seat, because they don't sell 2 tickets for the same chair in the stadium. The only way is if someone's got a fake ticket. Hopefully that's not the case, right? So we're going to assume that you don't have a fake ticket and they have the wrong seat because no one else can sit there if you're going to sit there. In an atom, the final number isn't a seat number so much. It's what we call the spin. And the spin quantum number tells us which way the electron is spinning. We'll talk more about that later too. It's probably the simplest of the quantum numbers to understand, really. So here are our 4 aspects of a ticket: the west gate, the section, the row, the seat. And in our atom, at the bottom, the principal quantum number, the orbital quantum number, the magnetic quantum number, and the spin quantum number. We're going to leave it right there for now. I'm going to talk again more about each of these quantum numbers and go into more detail about them. I just wanted to introduce them to you a little bit here, and then we'll dive into each of those a little more closely, and then start connecting it back to the periodic table a little bit, because it turns out the periodic table's shape, funny as it is, has its root in these quantum numbers. So more on that in the next video.